All right, so just gave you back your test. Let's go over it and then go over your homework as well. And we're going to finish rate law here. So for those that are not with me, you can open up your guidelines. You have this in your viewing pleasure if you want to. Okay, so the first question, very straightforward. They want for the millionth time a what? They want you to write the correct equilibrium constant expression. So they used to call it a law of mass action. Products of reactants, coefficients become exponents, and solid liquids do not apply. So my friends in chemistry, or my enemies if you hate this, that's all they want. But not everyone's taking the easy points. Okay, they're going to give you freebies. Grab a hold of them. I got some people forgot the 2. Okay, I had some people put a plus in between. Okay, so these are free points. Grab those. Equilibrium expression. And when we do acid and base equilibrium, which we're going to be starting tomorrow, it's going to be the same rules. It won't look like a KSP because you're not going to have a solid that you don't take in, but they'll be similar rules. Okay, any case, that's one. Now in B, they had a saturated solution. Now you need to understand, being saturated means the rate of the solid dissociating is equal to the ions going back. So you're at equilibrium. So they say they want the concentration. This is a classic KSP type question. Remember, brackets are concentration. So they want, what is the molarity of a certain ion? And the ion that I'm asking for is silver plus. Okay? Now, they drew an ice table here. This is not my work. This is AP Central's work. And I probably would have too if you're not seeing it, because people are not seeing it. Now, what does the ice table give me? It gives me the idea that stoichiometrically there are 2 silver ions per 1 chromate ion. Now, you probably don't need this if you can see it, but a lot of people didn't see it. So inside the brackets, this is going to be 2x. Why? Well, we're after the x. We're going to solve for x, which is what? The concentration of the chromate ion. Then we're going to have to what? Times it by 2 to get the silver. So this is 2x, this is x. And my friends in chemistry, classic AP problem, when you see an x and a 2x, or you see an x squared kind of a deal, this is going to make 4x cubed. 4x cubed. Why is it 2x? Because stoichiometrically, the value inside the brackets is going to be twice that of the value inside this bracket, because at equilibrium, one of these solids breaks apart into 2 silvers into 1. And people say to me, Mr. Grodsky, I feel like you're doing it twice because you're squaring it. The square is due to the equilibrium expression that gives you the K. The value in the brackets is stoichiometry always. Okay? So 4x cubed, and a lot of people didn't get there. Okay? They forgot that 2 there. And it's a classic one that's going to come up over and over and over. So 4x cubed, you divide this value by 4, take the what? The cube root. In your TI 84 plus West Hampton editions, okay, you're going to just do the math function and do the cube root. And now you get the value of x. Now, just putting 2x somewhere in your equation, I believe, gives you a point to show stoichiometrically you knew that Ag plus was twice that of x. So somewhere in your work, if you showed me stoichiometrically there was twice as much silver ions, I gave you a point somewhere. Now, after you solve for x, what is x? X is not silver ions. Silver ions is what? 2x, so you had to multiply it by 2 to get the final point. Okay, so very important you understand that. They gave you a point for recognizing the stoichiometric difference here. Something was 2x. So I needed to see that somewhere. That's why you see a 1 somewhere next to no answer. I said, oh, there's a stoichiometry. And then for the right answer. Okay? But to get partial credit here, it's not always the same way. I needed to take your bad value and times it by 2. So if you got like 1 out of 2, you didn't get 2 here, okay, I needed to see your bad value, your bad math, times by 2 to probably get the other point. But again, I'm always guessing sometimes because the rubric isn't always simple. I'd have to go back to the committee if I was grading to ask what we're accepting in this test date, and I wasn't there for that one. Okay, letter C was a disaster. They want the maximum mass in grams of the silver carbonate that can dissolve in 100 milliliters of water. I saw a lot of people start with the KSP. The KSP is not the concentration. People thought the KSP was a concentration of the solid. You can't do that. You don't have a concentration of a solid. All I have is the X that I just solved for. What's the X? The X is the concentration of the what? This 8.7 times 10 negative 5 is the concentration of the chromate ion. 2X is a silver. So we're dealing with what? Silver chromate. So how many chromates are in one of these? One. So I'm just going to use the X value. So I'm going to start with the molarity in the brackets, moles per liter of the chromate ion. And what do I do with it? Well, I'm going to take the moles per liter, and because they're asking for grams, somewhere I'm converting to grams, moles to grams. And I need a what? Formula mass. 1 point for using the formula mass or writing the formula mass somewhere in your problem correctly. Okay, so if you notice, if you have to convert to moles, you have no idea, convert to moles or grams in a problem, it's usually to give you a point for that. Okay, that's a gimme. The first question a gimme because they just want the expression. The second one right here is a gimme. Do the formula mass correctly, and most people got that point. Now what's happening here? I'm taking these moles, but this is per 1 liter. That was the molarity. So now I'm finding the grams per 1 liter. But they say how many grams exist in 100 milliliters of solution. So basically I'm doing what? Dividing it by 10, or dividing by 0.1 to find the moles per smaller solution. This is the moles, or grams I should say, of 1 liter. This is the grams of a smaller amount, so I'm dividing by 10. Okay? So they gave you a point for the right formula mass, no matter what you did with it correctly, and then a point for the right grams. You needed that there. And there's no partial credit for that. That's where the 2 from. You should have pulled at least the formula mass out. Okay. This was an important one. Okay? So in this question, they give you silver nitrate. Don't forget, you've got what? Silver chromate dissociating into 2 silver ions and that chromate ion. You're going to add silver nitrate. What do we know what silver nitrate is? It's going to dissociate into silver plus and NO3 minus. Hello, there's no NO3 minus in here. Has no effect. But what we just did, by adding soluble silver nitrate, we have increased the concentration of the silver. That's called a common ion effect. Le Chatelier's principle. Okay, if you want to go back to it, stress is too much Ag+. What's the reaction going to do? It's going to respond by lowering Ag+. How does it do so? Shifts that way. Makes more precipitate. Could you answer it that way? They'd accept it. Here's where you should be answering if you're a true college student, true college chemistry student. If I'm increasing A, watch party people, I'm at equilibrium. If I add too much A, K is products of a reaction just like Q, right? By adding too much products, is it now Q bigger than K? And the reaction is going to work always toward equilibrium. By adding too much products, because Q is products over reactants, you have too many products as compared to where the equilibrium position is for that temperature. The reaction works spontaneously in the reverse. So in my opinion, to make sure that you don't have to go back to committee to say, we're going to accept this, they were after Q was greater than K, so the reaction goes in the reverse spontaneously. And if you wanted to say it shifted to the left because it was a response by Le Chatelier's principle, that will work too. So notice they say in terms of Q or Le Chatelier's principle. But when you do Le Chatelier's principle, it's easy to mess that wording up. Yes?
So we only have like 40 minutes to do, like, we would have only had 40 minutes to do this whole thing.
Now, understand, you have 40 minutes generally. You have a long time to do 7 questions. So I'm giving you the timing. So you, in your mind, we're doing so many of these, I want you to have a clock in your head. How long should I be spending on these problems so that I don't spend 40 minutes on the first 10 questions, part 1. So the answer to your question is, it's about, if some questions you rip through fast, you'll have more time to go back. I'm not giving you that scenario. I'm just saying, let's learn what 20 minutes per one of these questions feels like so that you're at a good pace. And in truth, maybe the question 2 and 3 are easy for you and you need more time. You'll have time to go back. Okay, possibly. Okay, but you have to be in a good pace. I'm sorry to cut you off, though.
Do you recommend though that we skip like them if we have, or like if we don't know?
Here's my suggestion. It is a shame to spend time on a problem you're not going to get right and you can't figure out and not see questions that you do know. It is an absolute shame not to see the entire test first. Make sure that I can, what? It's a game. That test is a game to get as many points as possible. And if you're struggling and spending 10 minutes on one question, that's worth 1 point, and you don't get to 5 questions that could be worth a lot more points, okay, you can see that's not a good test-taking strategy. So you're bogging down, push it to the side, go on. Make sure you see every question. Make sure you answer every question you can get right correctly, and then go back to figure out stuff that's bogging you down. No one's perfect. To get about a 70% right gives you a 5. So there's going to be questions that you get tripped up on. You're under time pressure, constraint. That's why I'm doing what in class? I'm putting the stress on. That's why this time of year the stress is on. If I was to teach this stuff in a slower, lazy pace, we'd have to do what? Review it again. I'm in this frame of mind because it's pressure time. I want you guys to get this together. But you notice, if you're with me, I'm fitting this together. Yes, you're making mistakes, but I'm giving you what? Opportunities. So this is part of getting ready for that day. Okay, so getting back to that. Next question. Write a balanced reaction. Are you kidding me? Always write a net ion. Always write a net ion. So this is 1 point. My gosh, you can do that. So given the KSP, there's 3 of these to 1 of these, and there's your compound, 1 point and upset. So if you can't do a KSP problem, you should at least be able to go what? Do a formula mass, write the equilibrium expression, and help write this reaction. So 3 out of the 10 are gimmies. If you couldn't do anything else, you're pulling 3 points out of this. What do we want? What's the goal? 7. 7's the goal. But if you're getting 3 and you can do nothing else, you're not walking out with 0. There are points to grab in these. Find them. Okay. Many people did this very well. Okay. So now they have the KSP of that new reaction of Ag3PO4. Now it's going to be what? Cubed. Okay. They want to know the value of the KSP, which means we need to know the value of the what? Of the concentration inside. What did they give me? They gave me the concentration, the Ag plus in a saturated solution, which is equilibrium, to be this. Well, what's the ratio? 3 to 1. Wait a minute, there's 3 silvers to what? To what in the song? So there's 3 silvers to 1 phosphate, okay? So if I have the concentration of my silver, this has to be what at equilibrium? 1/3 of that, right? So you had to divide by 3. That's the stoichiometry. So take the value they gave you, divide by 3, and now you have the value of your phosphate. Plug it in and solve. So they gave you a point. You recognize that phosphate had to be divided by 3. Anyone not see why? Stoichiometrically. Now here's what confuses people. Classic KSP confusion. In the other problem, Mr. G, you put 2x and then squared it. Why isn't this 3 times this number and then cube it? Okay, people get confused with that. I'll say that again. People don't know when to make that 3 times. Now, what did they give me? They gave me this already, which represents the 3 times x. So you wouldn't do that again. This is the 3x in this case, the plus 3x. That's why this is what? 1/3 of that, the x. So this is the value of 3x. Now, if I was to give you the concentration of the PO4, which is x, what would you do to get the silver? Times it by 3, because that's the 3x. Okay? And then you just plug it in. So they gave a point if you took this and divided by 3. Recognize that stoichiometrically it's 1/3. Come on, we can do that. Then you plug in your values based on your KSP equation, and they gave you the point. Many people cashed in on those 2 points there. So that could be 5 already, getting close to our 7. And if you only get 5, 4, but don't do a 0. Don't do a 0. There's always questions to be had, all right? I'm not asking you to be perfect. I'm asking you the best that you can do. Now, this one, got a lot of people. What does saturated mean? Equilibrium. The rate of dissolving of that very, very insoluble compound is equal to the ions precipitated. Now, what did they say? I have a liter of a saturated solution. I have equilibrium of that compound. And now it evaporates. Water comes out. If water comes out, whoa! Is the concentration going to go up or go down? They're going to go up. If water evaporates, now let's see what we have here. Okay? Now, a lot of people were putting down a lot of algorithms. They were solving for the cures of different kind of, I don't know, they have all kinds of crazy math. But what do we have here? We have an equilibrium, and you don't have to write this, but I'm just showing you to teach. Okay, we had this solid in equilibrium with its 3 ions, and it's 1 phosphate. Okay, so what do we have here? All right, we have this happening. Now, when we do the KSP, we know it's Ag plus, coefficients become exponents, and that's equal to our KSP value. Now, what's inside these? What is inside brackets? Concentrations, molarities. Let's pretend these are 1 molar solutions. It's not going to be, but we're just going to pretend. Okay, this would probably be what, 3 molar, right? 3 to 1. Okay, now, what if I boil the water off or evaporates? Well, molarity is equal to what? If this is a molarity, and molarity is equal to mole over liter, the number of grams is not going away, it's the water. So the volumes are getting smaller, which means if your denominator gets smaller, your molarities increase. This might go to 3 point something higher, and this is 1 point something higher. You with me? Okay, good. Well, wait a minute. This is a K, isn't it? If both of these are going up, I'm no longer a K, am I? In fact, it now becomes a Q. There's more products than I'm supposed to have, right? Here's my K. If I have more products than reactants, what do I have? I've got a Q bigger than K. What happens? So, when the water evaporates, immediately the molarities are too high. So the reaction makes what? More precipitate to regain the same molarities. So you can do what? Molarity isn't just how many moles. There's obviously less moles in a smaller volume solution, right? But the molarity is going to stay the same. Why? Because at equilibrium, molarity is a function, or equilibrium is a function of temperature, not volume. You lower the volume, you will lower the number of moles of the products. The volume would be just as lower to maintain the same what? So that means it stays the same. Okay, so maybe you got that 20 minutes ago. You can always stop me. Okay, here we go. Rate law. You got to love rate law. You have to love rate law. If you did poorly on the KSP, this is where you cash in. It looks like it's really, really hard. These are the easiest questions. Now, you can't be a what? You can't be a robot. Mr. Grodsky, when I do rate law like this, normally I see another column of 2 reactants and I keep 1 constant. They're making it easier. They got rid of 2. They got rid of 2. All you have is what? The rate of disappearance. Here's your rate, molarity per second. The rate law only has 1 reactant. So now we have to do some math here. Is anything doubling and something else doubling or tripling or quadrupling? No. So you're going to have to do what? Set one reaction above the other. Now some people went some other, first of all, the independent variable. For those that don't know, height, doesn't height depend on how tall you are? So this is dependent variable is always here. The independent variable is always the x-axis. Okay? So we're going to change the concentration, which is independent, and we're going to watch how the rate, which is dependent upon this variable. So for those that didn't see that, back to just some basic science. The initial concentration of SO2, and that should have been a point you got. If you got messed up, who cares? But here you got 2 points. The best way to solve for what the order was is take one rate. Now I take the one that's bigger. And what does rate equal? Rate of the second equals the rate law of the second times the concentration to some what? So I found the rate of the second, times it by the k. The k's cancel because it's the same reaction. Okay, and now you have the concentration of S2O3 negative 2, which is in the first and the second experiment, over the first. And you see you'll get 1.5. And this is 1.5. So 1.5 equals 1.5 to some order is order of 1. That's the way you should have went. Now, are there other ways you could do the business? Absolutely. What are the other ways you could have done business? Well, I don't like mentioning this because people confuse this like they did on this test. But isn't rate equal K times the concentration in some order? Isn't that a slope? Yeah, so you could have gotten the K from doing a slope. So you could have done change of Y or change of X. I think that takes a lot longer from that. You could have justified it other ways. You could have mathematically said, hey, this is increasing by some amount, fraction-wise. This is increasing by the same amount, fraction-wise. Okay, and some people justified it using words. I don't see it that way, but you needed to justify. Some people say, hey, reaction order is 1. How come I get any points? Because you can't guess. They will not. There's 2 points to this. You must come up with 1, and you must need a justification, mathematically or something. You just can't guess. They won't give you ever a point for guessing. Now, if you said reaction is 2, because your math that you did incorrectly showed you 2, I'd give you the credit for saying reaction order of 2, although you'd lose a point for the justification. So that's different. You just can't throw it out there. They won't do it. They're smarter than you think. Okay? So you get 1. Now, that was 2 points. Now, they want you to solve for the rate. My friends in chemistry, this is where you make up points. What is the rate? It's K. Let's say you said it was first order. Let's say you said it was second order. Whatever you said that could be right or wrong, you put that in there. Pick any experiment. Put in the R, which is the initial rate of disappearance. Solve for K. K is equal to what? The rate. In this case, it was what? Molarity per second. If you said it was first order, that means molarity times itself is just molarity. Molarities go bye-bye. 1 over second over 1 is 1 over second. And you solve for it, and you get 0.4. You get a point for the right K based on whatever order you chose to be correct, assuming you use the consistent numbers that are in the same experiment. And you get a point for the right units. Okay? 2 points right there. They're always going to look at your units. And why do the units go bye-bye? Solve for K. Move them over. Now, if this was squared, check it out. The units are different. If you said it was second order, that means this becomes what? And then one of these m's cancel out, right? And this would be what? M to the negative 1, S to the negative 1. If you said this was cubed, 3 becomes 2, and now you got m to the what? 2. Obviously, it was first order. Okay, so it works out that way. So the units will be different. Spend time to get that point. That's an easy one. Okay? All right. Now, here's where people start falling apart. Now, I know time constraints were getting at you a little bit. And maybe in the real test, you could go back. And maybe on the real test, if you see a rate law, maybe I do that one first because I can get all the points out of that. If I don't get to the KSP, which I'm not going to be good at anyway, I save that for later. Who knows? My opinion is you've got to learn them all anyway. Now, here's the deal. In another trial, student mixed blah, blah, blah with hydrochloric acid. What do they say? Calculate the amount of what? Key word here. What is it? Time. Anytime time is involved, besides the rate and besides the unit, anytime you have a value, hey, it took 13 seconds. Or how much time does it take? Anytime they're talking about how long a reaction needs to get from some point to another, my friends in chemistry, you are dealing with the integrated rate law equation. Now, if you said it was first order, you go on your reference table and you go find the first one. They gave you a point for just setting it up. So this is a point right here. Point just plugging it in. Here you go. Here's 1 point. Time t, okay, of some time period, the initial concentration, the K that you solve for, and you solve for t. So they give you a point for just plugging those values in and then solving for t. And my friends in chemistry, if this was the first time you ever calculated with these equations and using the rules of logs, what are you doing? We've had 3 or 4 other opportunities. I know some people didn't know how to do the math here because they haven't done this question yet. Hello was a test. I'm giving you opportunities. So 4 seconds. So 1 point for just plugging in. Another for the correct answer. If you said it was second order, you'd have the one that is 1 over A minus 1 over A0 plus KT. And you plug in those values, you get a point just for setting up. There are points to be had here. All right? Now, this one drove me nuts. E, not E. E I understand getting wrong. So E was about, draw a new line here. And this is what last night was to help you with. Now, if you didn't get this right because I didn't quite get there, but this is a slope. This is K, isn't it? Now, you might understand this, but at a lower temperature, is the rate going to be the same? It's going to be lower. Reactions go lower. So you need it to be below this line and have a slope that's less steep at a lower temperature. Because we learned last night, rate law constants depend upon temperature and activation energy, correct? All right, so there's an example where that comes into play. And since that is a slope, right? Rate is equal to K. That's a slope here. The slope has to be what? Lower. And because the rate of reaction starting at a lower rate, your initial rate's going to be lower. Okay? So you needed to show that. And if you didn't get that, that's one you get wrong. I couldn't get that. Fine. But this one I'm going to go nuts about. Look at F. Based on what you decided the order was, 1 or 2. I can't believe how people didn't get this. Now, I know some people didn't get to it because you ran out of time. Clearly, Dan, back there, you ran out of time. All right? And you were crushing everything you saw so far. But we said it was first order. Draw me a graph that would prove that's first order. What were the lab about? I gave you a reaction. I want to know if it's first order, second order. When it was a straight line, that told you what order. So if this is first order, using the what? First order equation, ln of what? A of t minus the ln of A after some time period equals what? Not zero concentration equals a negative KT y mx plus b. So you put a negative slope straight line and your y is your ln of A. If you said it was second order based on your incorrect math, then I would suspect you would have 1 over that and have a what? Positive straight line. That's it. That's 2 points. That's it. Multiple choice. Not last night. Night before. Wasn't there one question that says which one proves it was second order? And it was the 1 over x line that gave you a what? Positive slope. I bet if I go back to see who got this wrong, who had the time, are the same people that did not do that homework. Okay, you've got to do what I've asked. But that's easy. Okay? So, any other questions? Always Monday morning quarterbacking. Oh, I should have, could have. This is where you make your mistakes. You look at this test and my gosh, this is so hard. When you see the answers, like, my gosh, how come I get this wrong? Because it just takes what? Practice. And I'm going to keep giving you practice. I'm going to keep stressing you out. I'm going to keep saying you got 40 minutes because this is how we get ready for the big game day. Okay? Not easy. Follow my plan. Do what I ask. Keep practicing. Keep figuring out your mistakes. I'm not asking you to get 10 out of 10. Okay, get the points you can have, and you can see all these points are doable. And by the way, so you know, I'm pulling every single hardest exam I could find. So when I sit you down for a quiz or a test, I'm giving you the hardest of all of them. Why am I doing that? Because if you get an easy question, you're going to just eat it up. I'm finding every one that I think is the hardest. And if you look at it, was it really that hard? No. Obviously, having the answers, things are easier. Okay. So I want to finish my time today what I talked about last night. Okay? What did I talk about last night? Something called the Arrhenius Equation. You don't have to be able to react with it, but we learned that the ln of K is equal to the negative E of A over the RT ln of A. And what does this mean? If all of my molecules are moving at different speeds. If my activation energy is right here, all of them would have enough energy or speed to overcome their negative repulsive forces and have the what? The energy to what? React. To go from here to here is what? Activation energy, correct? So that's activation energy. Now, if my activation energy increases, this is my E of A, watch. If I move my activation energy this way, isn't there a smaller fraction of molecules who now have enough energy, kinetically speaking, to overcome those repulsive forces and cause the collisions to have an effective collision? So if I increase this E of A, this becomes a bigger negative number. Now think about it. Ln of A is some number that represents a value for how big K is. If the activation energy increases, which means there's less molecules, now it's here, less molecules have the energy to overcome. It's kind of like doing this, making this hump higher. Isn't the rate going to drop? Why? This becomes a bigger negative, and this negative bigger value lowers this amount, and K drops. Think with me, party people. R is equal to K times whatever is inside to whatever order. If K increases, so does R. So if the activation energy gets higher, R does what? Okay, well, this becomes a bigger negative. K drops, and R goes down. Okay, but wait a minute. Is there something that gives me a lower EA? A catalyst. Lowers my EA, makes this a what? Smaller negative, makes my K bigger, and makes my rate faster. One more factor, which is based on your test too, temperature. If I increase the temperature, here's my EA, right? If I increase my temperature, this does what? Flattens out. Isn't there more chemicals now that have the speed? So if my EA now, just comparatively speaking, if temperature increases, the denominator gets bigger, the whole negative expression gets smaller, and my K increases. That's what that's about. The rate law constant is temperature sensitive and activation and basically EA sensitive, which is based upon either a catalyst, which lowers the EA, or inhibitors, which are reactants that increase EA. And real quickly, okay, my last point today that I showed you on the graph. If I look at all of this, and I look at these potential energy curves, this is a fallacy. This doesn't happen like this. Most reactions have mechanisms. This is the overall. So let's say I have X plus Y gives me XY, correct? Let's pretend it's one step. This would be the what? Activation energy of the one step. What if there's a mechanism? Let's pretend there's two steps. But what creates that new mechanism? Anyone? What creates the new mechanism? Right now it's a one-step process. A catalyst. By adding a catalyst, it creates a series of steps that are different. That's why adding a catalyst does what? Creates an alternative pathway. By adding a catalyst, now you have a couple of different what? A couple of different steps. All right? And now, my activation energy, okay, let's make it like this, a couple of different steps. And if I measure my activation energies of each step and add them together, now maybe if I add them together, instead of going all the way to the top, it goes where? It's here. So I lower my activation energy by using a bunch of series of steps that their collective activation energies added together is now lower. And now I've lowered the total E of A, which does what to my K constant? Lowers the negative value, makes the K higher. But I can add an inhibitor. Inhibitor is like a catalyst that starts a whole series of reactions, but this case, the series of reactions have bigger activation energies. So if you add the activation energies here, now it slows the reaction down because the total EA gets bigger. Okay? You have something to watch tonight, and you're going to do ditto number 1. Okay? Points to be had.